This is FE Peer Review, the Flat Earth Peer Review channel. The date is June 17th, 2020. This video is a brief look at the well-known platform habitat observation and sets out guidelines for how long-distance observations over water should be conducted in order to provide the most useful data. The platform habitat observation is frequently used by proponents of flat Earth to suggest we see farther than the globe model allows. I believe the original imagery was taken by BMLSB69 in 2016 and can be seen on his YouTube channel. Many people on both sides of the debate have gone through these observations with a fine-tooth comb, and I will refer to them while keeping my comments to a minimum. Does the platform habitat observation prove that we see too far? In a word, no. Not if the well-accepted and understood phenomenon of atmospheric refraction is taken into account. This can be amply demonstrated by using BMLSB69's data and checking it against the Bislin curve calculator. We will look briefly at his video here. He gives us the distance to the target, shows the observer location and the target location on Google Earth. 6 point something to the first platform and 9.41 miles to platform habitat. At this point in his video, we would jump ahead. BMLSB69 provides good but not complete documentation of his observation. He states his camera height as 1 foot above the beach, but there is a problematic moment where it appears he raises his camera as he is zooming out. He needs to address this point directly and should have done so in the video itself. It would have been helpful, for example, to mount the camera on a tripod of a fixed height and show the measurement of the height of the tripod to the ground. If he only has one camera to work with, he can actually just prepare the tripod in place with measuring tape, photograph the tripod in place, and then put the camera onto the tripod. Here is that moment where it appears the camera raises as he zooms out. This is where he is zooming to. And there we go. At that moment, what's that, 2:05, you can see that the angle of view of the water surface has changed quite a bit. We'll look at that one more time. I am not in any way suggesting that BMLSB was doing anything underhanded. I think if he did raise the camera, it may have been accidental. The point is a tripod would have avoided that kind of problem. And I'll take this moment to say one more thing about observations where the camera is set so close to the ground or water surface. In fact, if atmospheric refraction is a real phenomenon, which I'll come back to, the closer you set the camera to the water surface or the ground surface, the more the refraction effects are going to come into play. So if you want to eliminate or reduce the effects of refraction to obtain a more accurate observation of the geometric reality in front of you, you're better off not putting the camera 1 foot off the ground. Raise it up a few feet. Stand up straight, comfortable, put your camera on a tripod and point it straight forward. Whether you're 5.5 feet off the ground at eye level or 1 foot isn't going to make a huge difference in other respects of your observation. However, it will help quite a bit to reduce refraction. I'm now going to point out this moment in his video 2:17 where he has overlain a close-up photo of the platform And you can compare it to the video, and you can see the extent to which refraction is distorting his video. The most obvious element is this crane on the left. There's this huge bend in the crane, whereas the crane is actually straight. In fact, what you're seeing is an entire horizontal band from bottom of the crane up to that bend there that is stretched vertically. It's elongated vertically. Check the proportions between these two platforms, these two walkways over on the right here, and compare that distance to the distance to the top of that structure, and then compare that to the photo lower down. You see the two walkways, and then the distance to the top is much less. So what we're seeing is a stretching effect due to refraction in the video image. This means that a lot of vertical distortion is happening throughout the image. This should be clear. It should be clear enough from this that this kind of image cannot be relied upon for geometric documentation of these platforms. For a full analysis of how refraction is affecting this image, I refer to Walter Bislin's webpage. Walter Bislin has done a full analysis of the original images, as well as simulations based on different refraction effects. And he's got an extensive description of how atmospheric refraction works. I will also refer to this second web page here, which has a very nice simplified diagram that shows the basic concept of refraction. At a low refraction, we are seeing minimal amount of curve due to light. The geometric horizon is near the point that we are seeing as the horizon, whereas in high refraction conditions, the light reaching the eyes is traveling over a curved path. So not only are we seeing more of the platform, but we are seeing more of the water behind it. Refraction doesn't selectively pick an oil platform, raise that up, and leave everything else in place. It raises all the light rays. It bends all the light rays that are reaching the eye. So any light ray that's coming off of the surface of the water behind that platform is also reaching our eyes. Some flat Earth proponents reject language that describes two horizons, a geometric and an apparent horizon. This is essentially semantics. There are, in fact, two distances from the observer that need to be defined. We can call them whatever we want. Those would be the distance from the eye to let me rephrase that. The first distance is that between the observer's eyes and the straight line extending from them to the tangent of the sphere. Imagine a sphere with no atmosphere of any kind and a fixed radius. There is a fixed distance from the observer's eyes to a tangent point on that sphere. That would be the geometric horizon, or what some of us choose to call the geometric horizon. The second distance depends on there being an atmosphere and is variable as the atmosphere varies. So the geometric horizon, is dependent only on the radius of the sphere and the height of the observer. The apparent horizon is variable depending on atmospheric effects. Regarding the general acceptance of the reality of atmospheric refraction, I refer to the following two papers. The first is published on the Harvard University website and was written by a member of the U.S. Navy. This is Harvard EDU. This is the paper here. The second was prepared for the U.S. Department of Defense and is published by their Technical Information Center. This is the Technical Information Center of the Department of Defense, and it's under a .mil URL, which is the American military. I will not go through them in detail here. The references are available for anyone to read. My point is only to demonstrate the level of acceptance of the effects of atmospheric refraction. So I offer these guidelines to anyone doing long-distance observations. First, if your conclusions depend on not accepting the effects of atmospheric refraction as they are generally understood, you will need to provide substantial proof that the effects are either non-existent or being miscalculated by the scientific community first. Only once you have done that can you move to your larger conclusions. Second, document the height of your observation point as accurately as you can. Use a stable mount for your equipment. Document the distance to your target and your target dimensions as best as you are able. Third, unless you have already succeeded in proving atmospheric refraction does not influence your observation, take steps to minimize its effects. These include documenting weather conditions. Also, avoid placing cameras or telescopes inches from the ground or water surface, as this greatly increases refraction distortion. This will have the added benefit of reducing the interference of waves and swells on water observations. After all, the point of these observations is not to measure incidental waves, but rather the larger geometry of the Earth. Fourth, find locations where you can make observations of the same target from different heights, such as from the base and the top of a cliff. This will clarify to what extent elevation affects the observation. Fifth, repeat the observation on a number of different days, times of day, and weather conditions. This will help to clarify to what extent atmospheric conditions affect the observation. It may easily require 10 to 15 different observations of the target from the same location to obtain enough good data that conclusions can be drawn. Sixth, document your data, procedures, and equipment in such a way that it can be reproduced by other researchers. Lastly, if you think you have made an observation where you can see farther than the globe Earth model allows, do a full analysis of your observation, as it will be done by someone else using the globe model. Check your observation using such tools as the Bislin Advanced Curve Calculator and include refraction, because that is what others like myself will be doing with your observation until refraction has been disproven. I have analyzed several observations that claim to, quote, see too far, and in every case I have found that they do not. Over time, I will post these analyses. If you don't want someone else doing that kind of analysis to your observation and proving that current globe Earth theory accounts for it, then you will save yourself some headache by checking it yourself first. Thank you for watching this video. If you wish to see more like this, please subscribe.